But I'll probably do it again maybe on Thursday. I'm like I'm not wasting time. I'm spending way too much time on this one debate because I'm spending like 3 days on this.
It'll make you look good.
Yeah.
Thank you, but I think it's worth it. I think it's worth it. So.
So Wednesday and Thursday? Correct?
Jeremy, can you turn around? So here we go. This is home number. What number is this? 1. Yeah.
Homework 1? Oh, this is 4th quarter.
Yes. Guys, this is it.
Finally, 5 more quarters of school left.
This is it, guys.
Thank God.
No more Che.
Yeah.
No more Che.
Unless you teach.
Research.
Wait, you're teaching research next year?
I don't know.
Math
Teach
research.
BC next year.
All right, so here we go.
Just take AB if you teach it. That's rude.
Okay, number 1. The question is, find all solutions to the equation. Obviously, first one is 17.5. Second one using quadratic formula. You get conjugate pairs. Right? Now, if you expand this, the first question, you get cubic function, correct? Can you all agree with me? Can you all agree with me? By seeing and observing that the solutions, the complex solution to this particular cubic function is conjugate pairs, can you agree with me that coefficient of this cubic function when expanded will be real? Did you understand what I just said? Sure. I said, by observing that the complex roots, which are these two, since these complex roots are conjugate pairs, can you agree with me that when this expression is expanded into cubic functions, the coefficients of each term will be real? Right? Now, second question is, find a third degree polynomial cubic function such that that particular third degree polynomial will have same solution as the question number 1. First of all, is that even possible to create another cubic function with same solutions? Yes.
Can you just change A if it's like AX? Well, if it's like, you can just times the entire cubic function by some coefficient.
With n obviously does not equal to 0. For any real number you multiply to that expression, you will still have same solutions, yet different functions. So they're infinitely limiting in doing so. Right? What would the graphical interpretation of this multiplying n? Yet all these three graphs is something I'll have in common, meaning obviously the roots, but it's stretched in terms of multiply or reflection when it's negative and so forth. But they will all cross on the real axes the same points. Make sense? And their conjugate pairs will appear on complex plane. Correct? Now, how many solutions does x to the nth equals k have where k is not as 0 but real and n is a positive integer? Be careful how you answer this question. I want a complete answer, not partial. Okay, so what am I feeling that you would only give a partial answer?
N
Go ahead.
known solutions.
Chris.
N real and complex solutions.
Okay. Well, I mean, you guys are both correct. I mean, real and complex. But what I was trying to say is, you will get n number of roots in a complex plane, in complex number system, and you'll get up to n in real number system. Does that make sense? Right? Keep that in mind. So this question is, definitely asking for your understanding of applying the solution in different number systems. So make sure you know that. Sure. Given that x at the end equals k, where k is not equal to 0 and n is an positive integer, you will have n number of solutions, complex solutions, in obviously complex plane. Exactly n, including the multiplicity and so forth, which I'm going to talk about in a minute. But you get up to n in real number system. Can I move on? Simple concept. So, let me introduce you fundamental theorem of that sounds like stuff you should have learned long time ago. Fundamental theorem of algebra? Are you kidding me? But it's a bit involved for this to be introduced early on. When you took the algebra in like what? 6th grade? 8th? 7th grade? No, didn't you guys take algebra in 7th? Eighth grade, I'm sorry.
Like integrated algebra was
Okay. That's what I meant. It's not as fundamental as you think, in that sense of fundamental. Okay, so P of x is any polynomial of degree greater than equal to 1 with real or complex coefficients. Then P of x has at least one complex 0. Now, I mean, does this make sense? Does it really help us a lot with not much? Because we already know, depending on the number system, how many exactly, even though over real is at most. So it does say at least one complex 0. Now, when it says one complex 0, what does that mean? Which means a could be 0 or b could be 0. When it's a 0, you get an imaginary root. When b is 0, you get a real root. Okay, so this means either one, right? Complex or imaginary. Definition: suppose C is a 0 of a polynomial P of x. Degree P of x of degree at least 1. If C is a 0 with 0 roots of P of x, what can you tell me about P of C? It is equal to 0. Right? Now, the largest positive integer m such that x minus c to the m is a factor of P of x, then we say the multiplicity of 0 c of P of x. Does this make sense? No? Sure, one more time. If x minus c is one of the factors of P of x, we know c is a solution to the P of x. But what if x minus c is raised to a certain integer power? That means that root, we say, it has a multiplicity of m. Okay. Meaning, let's say 2, x equals 2 is a solution to the function x minus 2 to the square. You know the solution is 2, and the multiplicity is also 2 at x equals 2.
So like you get 2, 2.
Exactly. Like you want 2 comma 2's or 2 2's? Same thing. Same thing. Okay. Same thing obviously with function. When I raise the third power, that means you're going to get all 3 same roots of 2. 3 2's. 2 2 2. Okay. So at that point, got it? So multiplicity of 3 at x equals 2, multiplicity of 2 at x equals 2 also. So that's what definition of multiplicity is. You know this already, right? You guys, algebra 2 trait? Multiplicity? Okay. Raise your hand if you are not taking ACT 2.
For math
2C. 2. Level 2.
not doing it.
Level 1. I mean, are you taking both?
Oh, not taking
Oh,
I'm not taking level 1.
good. That's what I'm saying. So, everyone should take a level 2. Especially. In a sense, I would say in a sense it's easier than 1.
It's pretty easy.
Not only the curve is better, knowing you guys, and it tests you more on the concept of your understanding of your concept of new topics, instead of trying to trick you with trivial ideas. So it's it covers more topics. That's why it's in a way easier, because they don't go crazy on tricks on those concepts. They just want to see if we know this concept. And every single concept dealt in SX2 level 2 is dealt in this class. So by end of June you should be ready to go with vectors, matrices, polar, limits, talked about. I'm tutoring, so I know what topics there are.
Is it a bad idea to do it again?
You have to learn some of those topics on your own. Like matrices, you won't deal with it until towards the end. Vectors. I'm just saying, if it comes up, you will know. Or you could just calculator, or if you're not as 8, 9.
What we're doing is that we use matrices instead of macros.
The soup teach.
You tell him, Isaac.
Does soup use 89? No. Anyway. Just don't do this. Watch. Final zeros. What kind of question is that? What would you do first? Factor out x squared. That means x equals 0 will be one of the solutions with a multiplicity of 2. The rest, quadratic, comes out to be real solutions. Multiplicity of 1, so there's no point of even if it's. Now, question, that was example 0. That's why you didn't see this. It's not there. Here's example number 1. Don't copy this. Easy enough. Give a polynomial of degree 4 which has zeros as a following. What does this assume? Huh? Okay. What is that? Which means it assumes the coefficients of this particular polynomial of x with degree 4 have all real coefficients. Otherwise, I simply what? Just square this, or square that, or square that. For any one of the 3 roots to have a multiplicity of 2, which will make up the 4th degree polynomial. But that polynomial will not have its coefficients as reals. Does that make sense? Okay. Where's my stick? Alright. So, but if I assume that there are real coefficients for the degree polynomial 4, the conjugates has to be the part. And if you remember the homework question that I once gave you with that 3-factored term, I asked you to expand. Remember that? Okay. What was the whole point of that expansion? To show you that there will be non-real coefficient as one of the terms. And for those of you who did it, this question on the test will not.
Take the test.
Excuse me.
The question on the test is hard.
Yes, the question on the test, thank you, asked the question as to whether the conjugate zero theorem applies to the particular P of x, where it was written as x plus z and x, I thought it was plus z bar. Now, given this, what can you tell me about their coefficients of the P of x? Well, that's what you have to prove. Well, knowing this, if I multiply this out, what do I get? I get x squared plus, I think it was minus. I'm not sure this. I think it was minus.
Yeah, I think it was minus 2.
Yeah. So, was it plus? Just do either one. Alright, zx plus z bar x plus z times z bar, right? What will this give us? At least x squared coefficient will be real, 1. What is that? If I factor out the x, I get, it was minus. So if I subtract that, what do I get? If I factor out z's, I get z minus z bar minus product of z and z bar. We know z is, as defined in the question, any complex number. So it could be written in terms of a plus bi, where a and b are reals. So expanding this out, I get x squared plus this minus that is a plus b minus a minus bi, which will give you mm-hmm. You're right. It is plus. Thank you. Still people making a test and. So when you do that, thank you. We get 2a. This will be plus. So when you do that, you get 2ax, correct? When you add these two, you get, cancels out to 0, 2a. And you multiply it out, what do you get? A squared plus b squared. So therefore, a is real times 2 is real, so the real coefficient comes out, and also the a squared plus b squared is also a real coefficient. Therefore, we know, what do we know? That we found the theorem that when a solution is complex, it comes in complex conjugates. Right? And it shows you that because all the coefficients are real. To give a polynomial of degree 3 which has a zeros 3i and negative 4. Is that even possible? What am I talking about? What's the difference between this and the previous question? Well, obviously there's no room for conjugate because already, what, degree 3 given 3 roots. But is that impossible? Yeah. I'm emphasizing the point over and over again. It's the same concept over and over again. Okay? So what would be P of x? X minus 3 times x minus I times x plus 4. What will be the P of x for this particular case? And you expand them out and you'll see what